Manchester, 1911. Researchers working under Ernest Rutherford are conducting what they expect to be a routine experiment, firing a beam of alpha particles at a thin sheet of gold foil. At the time, the leading theory was J.J. Thomson's plum pudding model. It suggested that atoms were soft spheres of positive charge, with electrons embedded inside them, like seeds in a watermelon. Because the positive charge was thought to be spread thinly throughout the atom, these high-energy alpha particles were expected to pass through the foil with almost no deflection. This graph shows the actual data from the experiment. While most particles pass through as expected, about 1 in every 8,000 deflected at angles greater than 90 degrees, literally bouncing back toward the source. Rutherford was stunned. He remarked that it was as if you had fired a 15-inch shell at a piece of tissue paper, and it came back and hit you. To explain why the gold foil behaved like a wall rather than tissue paper, we have to look at the specific geometry of a single atomic collision. Zooming in to the microscopic scale, we see a single alpha particle, with a positive charge of +2e, approaching a gold nucleus. The path is defined by the impact parameter b, the perpendicular distance to the nucleus. As distance r shrinks, Coulomb's law dictates a violent repulsive force, deflecting the particle by a scattering angle, theta. Essentially, the impact parameter is the initial condition that determines exactly how much of that intense Coulomb force the particle will experience. When the impact parameter is large, the particle stays far away from the nucleus. Because the distance remains large, the repulsive force is weak, and the particle continues on with a scattering angle of nearly 0. But as the impact parameter shrinks, the alpha particle is forced into the intense electric field near the center of the atom. The massive increase in repulsive force results in a sharp, large scattering angle. In the rare case where the impact parameter is 0, the collision is head-on. The particle stops momentarily before reversing its direction entirely. These scenarios reveal a clear mathematical relationship. The scattering angle is inversely proportional to the impact parameter. If a smaller impact parameter leads to a larger deflection, why did only 1 in 8,000 particles bounce back? A head-on collision only happens when the particle is aimed directly at the center. The rarity of these rebounds suggests that the nucleus is a minute target compared to the total volume of the atom. We now know the atom is roughly 100,000 times larger than the nucleus itself. To put that in perspective, if the nucleus were the size of our Sun, the Earth's orbit would have to be 100 times further away than it actually is. This evidence replaced the pudding waddle with a planetary one, a dense, massive core surrounded by electrons revolving in stable orbits. While this explains the nucleus, it created a new problem. Classical physics couldn't explain why these revolving electrons didn't lose energy and spiral into the center, or why they emitted light at such specific, discrete wavelengths. These contradictions would eventually lead Niels Bohr to introduce quantum concepts to the model, fundamentally changing our understanding of atomic stability. But the first great mystery was solved. By simply measuring the angles of a target practice, Rutherford proved that we, and everything we see, are made almost entirely of nothing.